Let's look at the summary of results. Okay. So when I look at the summary of results, I'm going to talk about resistance, I'm going to talk about voltage. In fact, I think I'm not going to try to go too far. So let's start right here. What do I know about R series? That was 6 ohms. So if I look over here, if I have R parallel, we see that the big difference here is that R parallel is smaller than R resistance. Here's our series column, and here's our parallel column. So now, what about the voltages? So if I look at the voltages, I have that the voltage of the 2 ohm and the voltage of the 4 ohm are going to be what? This was 2.67 volts. This was 5.33 volts. And in this situation, we're finding that this is 8 volts, 8 volts. They're the same because they're in parallel. So now if I look at the currents, what do I see here? By the way, I should bring this up a little bit more to make it a little bit tighter. Okay, so if I look at the currents here, what do I see? Well, the currents for parallel should be all the same. So then I should, for series, excuse me, so I'm going to have I 2 ohms, I 4 ohms, I source, and if I look at these guys, this should be all the same, just like the voltages for parallel should be all the same. But that's not true for the parallel situation. We saw that this was 4 amps, 2 amps, 6 amps. What a dramatic difference. And then finally, we calculated the powers. And what do we have? We have that the power of the 2 ohm was positive 3.55 watts. That means passive. The power of the 4 ohm was positive 7.10 watts. And finally, the power of the 8 volt was minus 10.6 watts. And if I repeat over here, we get that this was 32 watts. This was 16 watts. And this guy was 48 watts. The power difference is huge. So let's box this up. So we can really compare these values here. And you gotta admit, that's a pretty dramatic difference. Really dramatic difference. So let's start the interpretation because there's a lot to unfold here. So the one thing that I would see here is that one can see a dramatic difference numerically between the two circuits. We see that all of the voltage in parallel is greater than all of the voltage in series. We see that I parallel is also greater than I series, and as a consequence, that tells us that the power of the parallel circuit was greater than that of the series. And that's exactly what we said up here. So if we come all the way up to the top, we talked about how the powers were going to be different. And we're seeing it firsthand. So in general, series is always smaller as well as the current. But in parallel, the voltages are usually bigger and the current is bigger. Therefore, a higher power output. So now let's come back and keep moving here. 2. So picture-wise, the power supply excuse me, the power supplies show a large difference. And what I mean by that is that the power of series, the output is about 10 point, what was it? I think it was 10.6 watts. Let me be careful here. Right, this guy is versus this one, the power of the parallel source. This guy is 48 watts. That's almost a factor of 5 times bigger. I think it's less than 5, of course, but it's about that. So what we're seeing here is that picture-wise, I'm looking at something like this. Playing the same game that we've played before. That versus this guy. What we're seeing here is that this guy is delivering 6 amps. This one is delivering 1.33 amps. What a huge difference in current. Gigantic. So what do we see? Well, in each situation for the power supply, note that their voltage is exactly the same. If I look at the source, that's the case. But what I'm seeing here is that I'm seeing that I have a small current, right? This is a small current from the series, whereas in parallel, I mean, it is gigantic compared to that, almost 5 times bigger. So therefore, if I look at the power of the series, the parallel power essentially has to be 5 times bigger. And the way we see this here is by calculating the ratio. So if we calculate the ratio, let's calculate these power ratios. So if I look at the power of the divided by the power of series, note that in this case, the voltages are the same. And they will cancel out. So it's really about the currents. So these guys are going to cancel out. So then this has to be, the power is 6 amps divided by 1.33 amps, and I get a ratio of 4.5. Now, to write out what that means here is it says that the parallel power supply puts out 4.5 times more power than the series one. Since this power must all be dissipated, one needs examples to put this into perspective. And we can do this with anyone. So let's look at an example. Our example that we want to look at is that we want to compare, okay, so we want to compare an incandescent versus an LED light bulb. Here's what we know. For an incandescent, bulbs, we find that if you, I gotta be careful when I say this here. So we're saying that if you pull these off the shelf in some store, you're going to see that their efficiencies are somewhere around 2.5 to about 5.5%. I've always used the worst value, which is around 2%, but I think it's a little bit higher than 2%. So this tells me here that we're going to make a rough average here. We're going to say 3.75% is our estimate. If we do the same thing with an LED bulb, so if you look at these percentages, again, you're pulling these off the shelf. They're not special ones, because there are special ones. You're getting somewhere between 25 to about 35. No, that's not right. It's about double that. It's about 50%. I should have checked this a little bit better. So if I do that, I'm going to say that that's, since we have 3.75, why don't we stick with 3.75? The middle point in this guy is 37.5%. What a crazy coincidence. I didn't realize that. So what does this mean? Let's just focus on the incandescent bulb. Let's focus on the incandescent light bulbs. Why do they say that I mean, just by looking at those efficiencies, you could see why somebody would want to go for LED. Because the incandescent bulb is dismal. They're both dismal, but it's better than the incandescent bulb. So when you look at the incandescent bulb, we then say on average, about 4% goes into usable light, visible light, while the remaining 96% is wasted as heat. So when you start to look at the powers of this, that means that the power of the 8-volt source, that has to go to what? Some power has to go to light, and some power has to go into heat. What do we mean by heat? Most of the time when we say this, we mean resistive heat. The heat that we are calculating now. So if you compare series and parallel to this, look at the numbers. Okay, so once again, we're talking about incandescent bulbs. So let's look at the total power. And this is in series. And then this is in parallel. So if you calculate the percentages of these guys, this is putting out 10.6 watts. This is putting out 48 watts. Therefore, if I look at the power just to light, it's a tiny bit. Only 0.4 watts actually gets to light up the bulb in series. But if we go to parallel, you're going to find that this is 1.8 watts. So we only see that 1.8 watts of power, not the 48 watts, but the 1.8. Where's the rest of it? Well, it goes into wasted heat. So you could see that the giant, portion of this is going into heat. And you could see why people would want to move towards LEDs. So when I start to look at this thing, here's what we say. Just by looking at these numbers, we then see here that if I have a higher power, I'm going to have a brighter bulb. Because we could see, if we come in here and we look at just the power of the light, there's more power in the parallel than there is in series. And as a consequence, we're going to see that the parallel bulbs are the brightest. And so if I look at the lower power, well, these are going to have dimmer bulbs. Just look at the power of series for light. It's 0.4 versus 1.8. So therefore, series bulbs are dimmest when you compare them. Now, because it's brighter, there's more power coming out of it in parallel. It turns out that these will last a shorter time because there's more energy going through it. And on the other hand, these will last a longer time because there's less energy going through them. So one of the things that I want to look at is that I want to look at a FET circuit. And this is again in the lecture links. So let's go look at that. Let me make sure that I'm set up. Okay, I am. And here we are. So I haven't connected them, but you see I have a battery. So I'm going to pull a wire, and I wanted to show some of it with you. All you do is that you pull stuff off, and then you can just connect them. That's what I did with the light bulbs. So I'm doing this just to try to make things as fast as possible. Now I'm going to connect this guy here. So I just have one more wire to connect. So now if I come in here and I do the same thing for these guys, but now I'll do them in parallel. So now let's start connecting these guys. So here we go. Okay, look at the brightness of the series. And the way you talk about the brightness is you look at the lines, the number of lines, and look at the speed of the electrons. The drift speed is slow because it's a lower current. Now look at this guy. Look how bigger the lines are emanating from the bulb. Look how much faster the electrons are moving. They have a higher drift velocity. And if I come over here, you see, I'm actually running more current through the power supply than I am in series here. So let me capture an image of this thing and go back, and what I have here is that I have this guy. So just by looking at them, you could see here is that this guy right here is dimmer. These guys right here are brighter because the lines are larger or longer, excuse me. So once again, series implies dimmer, just as we expected. Parallel is brighter, and that's what we're seeing. There's a video that I'm not going to go through, but I think it's worth seeing, and it's linked. So there's a YouTube video that I linked, and it's called Series and Parallel Light Bulbs. And what you see here is that you see this, they do this in live, but it turns out that they spend too much time on it, and I was going to edit it. But look at that. This is in parallel. This is in series. See the dramatic difference in the brightness? You should. And then one last thing before I stop here is that series circuits only have one path, while parallel circuits have multiple. I think I spelled that wrong. Multiple. Oh, there's no O there. Multiple paths. So the one thing that we should do here is that we should go back to that circuit here. Let me make sure because, yeah, I'm there. So now that I'm here, look what you want to do here. So if this has only one path. So if I take any wire off, all current stops instantly. It actually takes the speed of light. If I take one wire off, this guy continues to flow because it has multiple paths. So that means that if we come back into the screen here, if I remove one wire here in this guy, you're seeing that it creates an open circuit, and that stops all current. But that's not true for parallel. And the reason why it's not true for parallel is because you have multiple paths. So here, it's not an open circuit, but we have multiple paths in parallel.